Hello, you don't know this, but I just made an entire video where I evaluated the limit as beta approaches 0 of 1 minus cosine beta over beta squared with one small mistake in it, so I'm re-recording it, and hopefully this version will be accurate. Whenever we're evaluating a limit, we always want to try substitution, right? That's a real easy-to-use technique that sometimes gives us the value that we're looking for. So we try that with this limit. We put 0 in where the betas are located. Those are supposed to be betas, by the way. Unfortunately, in this case, what we end up with is 1 minus 1, which is 0 in the numerator, and 0 squared on the bottom, which is also 0. You know this to be called an indeterminate form. And the good news is, usually these work out to be a real value, at least with the problems we've been working with. So there's a good chance that we can find the limit in this case. What we're going to need, though, is a trig identity, because with these problems we've been shooting for trying to match up like sine of theta over theta when the limit goes to 0 so we can make 1, right? And as you can see, there are no sign of betas in this problem, so we're going to have to transform this thing. If you look through your trig identities, you'll probably see this one, which is the one we're going to use, usually written something like cosine 2x equals 1 minus 2 sine squared of x. Now, we do have to take one thing into account, that our problem has beta where the 2x is. And that means that when we need x, that's really beta divided by 2. So we are going to rewrite our original limit using this identity, just being careful to include beta over 2 instead of x. So let's do that, and then we'll see if that helps us. So we want to evaluate the limit as beta approaches 0 of 1 minus the thing in the circle, which is 1 minus 2 sine squared of beta over 2. Remember where that x is in the identity, we need a beta over 2. And the beta squared is still on the bottom, okay, in the denominator. Alright, so did that help us? Well, it turns out it did. We can simplify the numerator and make this limit as beta approaches 0 of 2 sine squared beta over 2 over beta squared. I just started a new slide here to give us a little more room, but as you can see, we do have 2 sine squared beta over 2 divided by beta squared, and we're going to take the limit as beta approaches 0. Now, we can use our limit laws to simplify this a little bit and zero in on what we're really looking for. First of all, that constant multiple of 2 can be pulled out. Where's my pen? Here we go. And since, let me write that down so you can see it. My brain is ahead of my pen here. So we have 2 times the limit as beta approaches 0 of sine squared beta over 2 over beta squared. Notice that the numerator and the denominator are both squared, so we can actually write this limit in this form. Limit of a square is a square of the limit. Limit as beta approaches 0 of sine beta over 2 over beta, and we'll square the whole thing. And now we can use our little trick of multiplying by a form of 1. In order to use our theorem, limit as theta approaches 0, sine theta over theta is 1, we need to have a beta over 2 in the denominator. And so I'm going to multiply by 1/2 in the denominator, but I also have to multiply by 1/2 in the numerator, so I don't change the value. Okay, so, and then we can write this as 2 times the limit as beta approaches 0 of, I'm going to factor out the 1/2 sine beta over 2 over beta over 2. We know this thing turns, that's squared. We know this thing turns into a 1, the limit, the value of the limit. So I can squeeze it in on the screen if you don't mind. I have 2 times 1/2 squared, which is 2 times 1/4, which is 1/2. So for this particular limit, that weird indeterminate form 0 over 0 has a value of 1/2. Keep up the good work. Be patient with yourself. Don't panic. These are challenging, mainly because the algebra and trig are things that we don't use all the time, and so it takes a little brushing up to get this. But the concept of the limit is the same. And if you view this on a graphing calculator or with graphing software, you'll see that we do have this limit as beta approaches 0. I'm going to show you that on the next slide. So as you can see here, I've graphed our function. Now I changed the betas to x's so that I could use the Desmos graphing calculator. But what I want to point out to you is that as we approach the x value 0, the y value is in fact heading towards 1/2, 0.5 on our graph here. And that's what we're checking. We're checking to see as this graph gets closer and closer to x equals 0, what y value are we zeroing in on? And since it's the same on the right and the left, our graph does support our calculation that the limit here is 1/2. Good luck with the rest of your work.